This is Krishna Adury, and today we are going to learn about optics as given in 10th class portion, okay, grade 10 students. Now we are seeing this electromagnetic wave, we call this EM wave. Light travels in the form of electromagnetic wave. We all are familiar with mechanical waves and electromagnetic radiation, the difference between these two. Sound travels in the form of mechanical waves because sound needs a medium also. Like unless you have some material medium, sound cannot travel. Sound needs a material medium and sound cannot travel through vacuum. So, but whereas light, we are at a distance of 150 million kilometers from the sun. Despite that fact, light can travel through vacuum and we get light, and you know the speed of light, it travels very, very fast. In fact, it takes only 500 seconds for light to reach the earth once it starts from the sun. Okay, 8 and 1/3 minute there like. So when you look at how does light propagate, so you should understand the nature of electromagnetic wave. As you see here, there are two different fields, electric field and magnetic field. These two are perpendicular to each other. You can see the electric field here, it is in XY plane, and the magnetic field here is in XZ plane. So these two fields are oscillating electric and magnetic fields, and that should be remembered. And light travels in a direction which is perpendicular to both of them. So when you look at the EM wave, you understand there are two oscillating fields, electric and magnetic fields. Electric field is in red color here and magnetic field is in blue color. They are perpendicular to each other, and electric field is in XY plane and magnetic field is in XZ plane. And the light travels in the direction, in this x-axis direction, light travels in a direction which is perpendicular to both the fields there. So before we embark on learning about light, we should understand the nature of light. So light travels in the form of electromagnetic radiation. Okay, then we now go to a concept like refraction. What happens when light travels from one medium to another medium? As you see here, you have got air here. This is air, rarer medium. The density of air is less, and beneath that you have got water. You can see this in blue color. And you have air here, you have water here. In case you have air all through, there is no change in the medium, light travels straight. Okay, this you can understand. There is no deviation in the path of the light if there is no change in the medium. It straight away goes from air and it is entering air. There is absolutely no deviation there. But when you think of water and the ray is coming from air and entering water, you say that the light ray is coming from rarer medium and entering denser medium. It is entering water. You can see the deviation here. There is there is a bending of light ray. And there is one critical point here which you have to watch. When you are studying this refraction at the surface where the light ray incidents there is a bit of reflection. The point that one must notice here is that though you are studying refraction, you can't completely ignore reflection. There's a little amount of air at the separation of the media coming back into the same medium, and that is reflection. And now we are keen about what happens when it enters the other medium and how does it change. So now at the point of incidence where the light is falling, we are drawing a normal, because this is perpendicular to this surface. This angle is a right angle there. So the angle between the incident ray and the normal drawn is angle of incidence. And similarly, angle between the normal and the refracted ray here, this angle is angle of refraction. I can even think of measuring the angle of incidence and angle of refraction. Okay, this is somewhere around 40 degrees, this angle of incidence, but the angle of refraction is only 30 degrees. So as the refracted ray is bending towards the normal, angle of refraction is less than that of angle of incidence. So when a ray is entering from rarer medium to denser medium, the bending of light ray is towards the normal. This is an important point here. Now let us see now what happens if I take denser medium on the top and beneath you take, say, a rarer medium. It is something like the ray is coming from water and entering into air. So that change I make, and let me keep this measuring for a while there. It is water now. Now there is no deviation because it's from water into water. Okay, there is no change of medium, but I want to take air here. Like now I want to tell you something which is even more significant here. There is no refraction taking place. Absolutely, the ray is not entering the rarer medium. The reason is quite simple here. The angle of incidence here, the angle between the normal and the incident ray, this angle is more than the critical angle. So this we studied as a phenomenon in earlier classes, that when a ray enters from denser medium to rarer medium, when a ray is entering from denser medium to rarer medium, when the angle of incidence is more than the critical angle, the ray does not enter the rarer medium. It goes back into the denser medium. Okay, you have studied the examples of mirage or, like diamond, what happens inside, because, the brilliance of diamond. All these are examples of total internal reflection. So my point here is, if the angle is less than the critical angle, certainly what you can expect is the bending is away from the normal. This angle is angle of incidence, angle between the incident ray and the normal drawn at the point of incidence. This is angle of incidence. But look at the angle of refraction. That looks greater. Angle of refraction is larger. So the bending is away from the normal. Let us think of measuring these two. So if you keep, this is around, say, 35 degrees there, angle of incidence. But whereas this angle of refraction from here to here, it is near 40. So you should understand that angle of incidence is less than that of angle of refraction. And why does this happen? Because the ray is entering from denser medium to rarer medium. And therefore the point is, when the ray is entering from denser medium to rarer medium, angle of refraction is larger than angle of incidence. And effectively the bending is away from the normal. Okay, this is a critical point we are observing here, angle of incidence and angle of refraction. And there is another aspect that we can study here. Let us say, like how does light refract, particularly when you take, say, you are taking a prism and the light is made to pass through that, and you can see the refraction happening twice. Means it is entering from air into glass, and from the glass it is coming back into the air. So the change of medium is happening twice, air into glass and again glass into air. Therefore the bending is observed twice. Okay, this a point you should understand. And what I also can show you is that the light ray, what you see in red color, is because of, see, the red is of the wavelength, because wavelength determines the color of the light. Okay, what we can rather see is that it is only the visible light, which is 400 nanometers to 700 nanometers, or you can say 4000 angstrom units to 7000 angstrom units. Only when the wavelength is in this range, you find all this visible light and different colors and all that, like, And when I change that color, you can observe that the wavelength is about 400 nanometers. That is, say, blue color, and violet at the end. And as you move this side, okay, you get different colors, and finally you land up at red. You know that it's from Vibgeo, or like violet indigo. So violet you find at this end, wavelength is very less, frequency is more. And when you go to red, frequency is less, but the wavelength is maximum. Okay, it's about 700 nanometers. So you can change the colors, whichever is the color, you see that the bending is taking place. But there is a difference, like, the bending in all the cases is not the same. So what happens here is, there is, like when you look at the dispersion of light, let us say, make that background completely black, you can observe here here you see the dispersion of light, okay, and red color is bending less, and whereas the violet color is bending more. In fact, I can say it's a blue color bending more. So why this difference comes actually, like, because it's a light ray, like is getting decomposed into different components and all that, like, you have varied components. When you send a monochromatic light, like a single colored light white, that white color gets dispersed into different colors. Okay, you see red bending slightly, and you see blue bending to a large extent and all that, like, so now you also can think of why does this happen actually, like, I am not able to count all these colors. I mean, I'm not able to identify all the colors. So the reason is quite simple. However narrow you take the slit, okay, the ray coming from, it's a beam of rays. It's not a particular ray. It is a beam of rays. It may be narrow beam, okay, it's okay, it doesn't matter much, but it's a narrow beam, but it's a beam, and therefore you have a number of rays coming close to each other. And then what happens here is these different rays which are forming the beam, they refract in differently actually, and therefore due to overlapping of all these colors, it is very difficult to identify all the 7 colors, okay, and therefore the spectrum what you are getting, if you want to observe all the 7 colors, in many cases it's not possible. It is an impure spectrum what you are getting. Okay, a pure spectrum is an ideal condition where you can see all the 7 colors, but due to overlapping of these colors, you can at most identify 4 colors. This is what we mean by dispersion of light. Okay, and I just want to show you the beam of rays now, and this is what we mean by a beam of rays. A number of rays close to each other, they are coming and refracting twice and coming out of this, emerging out of this prism, and this is what we mean by refraction at a prism. Now I am going to talk about a spherical lens and a spherical mirror. Okay, spherical lens and spherical mirrors. We have a biconvex lens here, and this biconvex lens has got 2 centers of curvature on either side of it, and usually these 2 centers are at the same distance, and they can be at different distances also if the radii differ, because if the radius on one side surface is R1 and the second side is R2, and definitely the centers of curvatures can be at different distances from the center of the lens. Like, anyway, you have here the center, and this point is principal focus, and this is principal axis. The other side also you got the principal focus, and again you got the center of curvature here. Now I am taking the object here, and the object is kept closer to the lens, okay, very close to the lens, at a distance which is less than the focal length. In this case, what happens is you can find the image formed on the same side of the lens. It's a magnified image and it's a virtual image. Generally, this convex lens is used as a magnifying glass. But if you want to watch anything using this magnifying glass, the object must be placed at a distance less than the focal length. It should be close to the lens. Okay, and when you want to watch anything which is, like very small in size, you can read a text which is, the font size is very less and so on. Like, when the object is at a distance less than the focal length, the image is formed on the same side. It's a magnified image. It's a virtual image. Okay, and this is the first case. Later, if you take the object and keep it at the focus, so what you can watch here is that the rays emanating from that, coming from the lens on the other side, of course, they're all parallel lines. We don't know where they are going to meet. And therefore, the image is formed at infinity, like, where all these parallel lines, almost parallel lines, they converge. And we don't study the properties in this particular case because the object is placed at the principal focus, but the image is formed at infinity. So you leave this case, and when the object now is placed between F and C, between the principal focus and the center of curvature, you can see the image formed on the other side, but it is beyond C. And what you can watch here is that it is a real image, it's an inverted image, But mind you, it is a magnified image. Okay, the size of the image is larger than the size of the object. And the properties here you can say, consolidate and say that it is a real image, it's an inverted image, it's a magnified image. Now I am taking a case where the object is placed at C. When it is placed at C this side, you can see the image is formed on the other side. It is also at C. But how is the image? It is a real image, it is inverted image, and mind you, it is of the same size. The object and image here are of the same size. Object is placed at C, the image is formed at C, and here object distance and image distance are the same, and not only that, the size of the object is same as that of the image. Okay, but when you take the object a little farther, and now the object is placed beyond C, and the other side you can see the image is formed between F and C. And the important point you have to observe here is that the size of the image is less than that of the object. So it's a diminished image. Size is smaller. So where is it? It is between F and C. It is a real image, inverted image, and it is between F and C, and the size is less than that of the object. It's a diminished image. But there is one case we need not watch, of course, when the object is taken much farther, placed at infinity. What generally is seen is that the image is formed at the principal focus. Okay, these are interchangeable. When the object is placed at F, the image is formed at infinity. And when the object is placed at infinity, generally we don't place, we see only the distant object, maybe a distant tree or a building. And when you put the lens there, the image is formed at focus. And the size of the image is much smaller, and therefore you say it's a point size image. Okay, much less, it's insignificant, the size of this is. So when the object is placed at infinity, the image is formed at F. And when the object is placed at F, the image is formed at infinity. So this is what you have to notice. And this is the biconvex lens we are talking about. And let me take, say, a convex lens, a concave lens. Okay, and you can identify the concave lens very easily. Like when you have, it's thin in the middle and thick at the edges. That is what we mean by a concave lens. Okay, a biconcave lens. Now here, the images formed are of the same category. Okay, you need not study different cases, all the cases differently. Whether you place the object close to the lens, or whether you place it at F, or whether you place it between F and C, or beyond C. In all the cases, the image is formed on the same side. The image is smaller, and it is a virtual image. And therefore, all the images formed due to concave lens are virtual images. Okay, they are no real image. Okay, no image can be caught on the screen. And this is the important one like this. So there are no different cases that you're going to see. Let us move on to a mirror. Okay, when you take concave mirror and the image is formed due to reflection, and let us understand the first case when the object is placed at a distance less than the focal length. This is a concave mirror. You see the image formed on the other side of the mirror. Okay, it's appearing much larger. It is a virtual image, erect image, not inverted. It's an erect image and much larger in size. Because of this property, okay, when the object is placed at a distance less than the focal length, the image is formed on the other side, which is much larger. This concave mirror is used as a shaving mirror. When the mirror is placed close to your chin, at a distance, the chin is at a distance less than the focal length. The chin appears much larger in the mirror. It is an erect image, and therefore concave mirror is used as a shaving mirror. But the condition is that the chin must be placed at a distance less than the focal length. And let us take the case when it is at, say, F, principal focus, and the rays are parallel, almost parallel. We don't know where they converge. So we don't study the properties of the image formed when the object is at F, because it is formed at infinity like. But take it a little beyond. When the object is placed between F and C, the image is a real image, it's an inverted image, and it's a magnified image. I repeat, when the object is placed between F and C, the image is formed beyond C. It's a real image, inverted image, magnified image. Let us take the object in a little farther. And now it is at C. When the object is at C, the image also is formed at C. It's a real image, inverted image, and now look at the size. The size is almost that of object. So object and image are of the same size when the object is placed at C. But when you take this object, take it a little beyond, the image is formed between F and C. So object is moving farther, the image is getting closer to the mirror. There's an important observation you have to notice there. So when the object is placed beyond C, the image is formed between F and C, real image, inverted image, and important point, it's a diminished image. The size of the image is smaller compared to the size of the object. Real, inverted, and a diminished image. And there is one case which you have to consider. When the object is taken to the infinity, like very, very long distance, and the image is formed at F, and probably the size of the image is much, much smaller. It's a real image. It's a point size image. So this is how we can study the properties of the image formed due to a concave mirror. But when you take, say, a convex mirror, the properties, it's much easy for us because it doesn't vary much with the position of the object. Let us understand whether the object is close to the mirror or whatever be the distance, wherever you place it, the image is formed which is much smaller. It is virtual image, it is erect image, it is always the diminished image. And therefore, this convex mirror is used as a rear view mirror of a driver. So the driver is looking at the vehicle which is coming from behind, and the vehicle appears in the mirror much smaller. Mind you, it appears to be closer, and it is always a virtual image, erect image. If you use an ordinary mirror as a rear view mirror of the vehicles, you can't see the complete picture of what's coming behind. Okay, and therefore you have to necessarily use a convex mirror as a driver's rear view mirror, which tells you categorically that the size of the image is less, but mind you, the vehicle appears to be much, much smaller. And this is how we can study the properties of the images formed by convex lens, concave lens, concave mirror, and convex mirror. Thank you very much.